a tight time schedule because we have to move into the other building for Andy Strominger's talk. So let's start with the first speaker. It's a great pleasure to have Shiraz Minwalla from TATA Institute. He'll talk about black hole dynamics at large D.
Okay, it's really nice to be back in Israel and I think so. Yes. It's really nice to be back in Israel, to be in Jerusalem, and once again, Rajesh Penta and I went to the old city yesterday, and it was so fantastic. Yeah. Okay, my talk today is titled Black Hole Dynamics at Large D, and is based on two papers that we've put out in the archive, along with ongoing work, and it builds on observations and earlier work and concurrent work by Emperan, Suzuki, Tanabe, and collaborators. Okay, so let me start with an introduction. As all of you know, about 3 weeks ago, the LIGO collaboration reported the discovery of gravity waves. The waves they discovered were created in an awe-inspiring event, at least if we believe their analysis. The event that is described is one in which two black holes, each of about 30 times the mass of the sun, bang into each other, and in that process they released about 3 solar masses of energy as gravitational waves. Now let's just to get a sense for the numbers, let's look at the time scale for these processes. So a black hole of size 30 solar masses has a Schwarzschild radius of about 100 kilometers. The time scale for the collision is set by this length scale. Okay, so the time scale for this collision is given by the time the light takes to cross 100 or maybe 200 or 300 kilometers, which is about 10 to the power minus 3 seconds. So in the collision that we're talking about, 3 solar masses of energy were released in about 10 to the power minus 3 seconds. Okay, now just to get a sense for that, let's remember that the sun, through its career, will release about 1% of its rest mass, and its career spans 10 billion years, okay, which is about 10 to the power 17 seconds. Okay, so this process here releases 300 times as much energy as the sun will through its whole lifetime in about 10 to the power minus 20th the time. Okay, to get a better sense of the nature of these numbers, let's remember that in our galaxy we have approximately 10 to the power 10 stars, 10 billion stars, and the number of galaxies in the visible universe is about 10 to the power 10. So the intensity of emission from this bank was about 100 times as large as the integrated intensity of emission of light from all stars in the visible universe. So it's quite an event. Okay. Now, black hole collisions are certainly not the only dramatic events in the universe.
Shiraz, you're just jealous.
Of the black holes?
Of the energy.
Now, black hole collisions are certainly not the only dramatic events in the universe. For instance, supernovas, quite dramatic, they release a lot of energy. However, from the point of view of theorists, there's something much nicer about black hole collisions than supernovas. And the nice thing is that supernovas are pretty dirty events. They're complicated events. They're events like solid state physics. Worse. Okay. Okay. On the other hand, black hole collisions are governed by this parameter-free equation, which is probably the most, in my opinion, the most beautiful equations written down by human beings. Okay, so this collisions, extremely energetic, awe-inspiring event is governed by a very simple equation, so it should be completely amenable to theoretical analysis. Okay, great. So in order to understand black hole collisions, all we have to do is to solve Einstein's equations with the appropriate boundary conditions. However, that's not as easy as it sounds. You know, the way LIGO analyzes all this is for the early part of the collision it uses post-Newtonian approximations. Then things become nonlinear and they switch over to numerics. Okay? In order to switch over to numerics, in their code they use the results of 10,000 full simulations of general relativity. And that sounds like a lot, That sounds like a lot of simulations, but just to get a sense of how much that actually is, let's remember that there are 9 parameters in the initial conditions of black hole collisions. Now 10,000, which is a big number, is just 9 to the power 4.2. So if you discretize your 9 parameter space and put points on the grids, each parameter will get only 4 points. Okay? Now suppose you want to increase 4 to 5, you'd need 60,000 simulations. If you wanted to increase 4 to 10, you'd need 3 billion simulations. Okay? These simulations are all difficult, time consuming, and so densely filling out the space of parameters is just not practical. Okay? So this attitude of just take the thing and dump it on a computer is not completely practical. It also sounds tasteless. So what we're going to try to do in this talk is try to see if a theorist can help understand these dramatic events. Okay. So given a complicated problem that you want to solve, the natural instinct of a theorist is to try to find a parameter in which to do perturbation theory. Okay? In this talk, what we're going to try to follow that instinct. In this talk, what we're going to try to do is to follow the lead of Emperon, Suzuki, and Tanabe, and to try to use 1 by d as a perturbative parameter, where d is the number of space-time dimensions. I want to emphasize that my talk will be entirely classical. There's no quantum mechanics. All I'm trying to do is to solve Einstein's equations using an approximation scheme. My perturbative parameter is 1 by d. D is the number of space-time dimensions. Okay? Now, I don't yet know if this expansion will be useful for d equals 4, because that's a bit touch and go, because d is 4 is big or small depending on details. Okay? However, interestingly enough, the reformulation of black hole dynamics at large d turns out to be given in terms of the dynamics of an auxiliary membrane, and this I will describe to you. Okay? So I will hope to convince you that the structures we encounter in this attempt are interesting enough to justify the attempt, even if d equals 4 doesn't turn out to be big enough for this to be practically useful. Okay, so let's start. Let's take a look at the Schwarzschild black hole in d space-time dimensions. The metric in Schwarzschild coordinates is given here, and is characterized by the so-called blackening factor. Now, Emperon and Suzuki and Tanabe made the following important observation about this metric. Suppose we look at this blackening factor, we hold r fixed at a value greater than r naught, and then take d to infinity. This thing becomes a number less than 1 to the power infinity, which is 0, and so the metric reduces just to flat space. So what we realize is that in an infinite number of dimensions, if we hold where we are looking fixed and take d to infinity, outside the event horizon we just see flat space. This is of course a reflection of the extremely fast fall off of the Newtonian potential in large d. Okay. Now, in order to see that there is a black hole, how near to the event horizon do we have to go? Emperon, Suzuki, and Tanabe realized the following. Suppose instead of holding r fixed, you scale r to be r naught into 1 plus capital R by d minus 3, and hold capital R fixed as we take d to infinity. Then, using the fact that this quantity is this in the limit that d goes to infinity, we see that now we see the black hole. In other words, if as you take d to infinity you simultaneously scale towards the event horizon so that you stay within a region 1 by d of the event horizon, you start seeing that there's a black hole. Okay? So the moral of this story is that black holes become very thin in large number of dimensions. They have 2 length scales. The first length scale is their size, which is r naught. The second length scale is a much smaller one, which is their thickness, which is r naught by d. Okay, now Emperon, Suzuki, Tanabe did more than this. They proceeded to do an actual calculation associated with these black holes at large d. What they computed was the spectrum of quasi-normal modes of this black hole. Now, the spectrum of quasi-normal modes actually turns out to be very intuitive. To understand that it's intuitive, we've seen that the black hole is like a thin shell of radius r naught. Imagine solving a minimally coupled scalar equation in a thin shell of radius r naught with some boundary conditions at the 2 edges. You see there are 2 length scales. There's one over the thickness and one over the radius. Most solutions will have masses set by 1 over the thickness, because most solutions will wiggle in the thickness direction. However, depending on boundary conditions, there might be special solutions that don't wiggle in the thickness direction, where modes will be set by 1 over the radius. Okay, and indeed this is exactly what Empron and Suzuki and Tanabe found. They found that they had two kinds of modes. The generic mode had frequency 1 over the thickness, which is d by r naught. Okay, however, there existed a special set of modes, okay, that had much lower frequencies of order 1 over r naught. So now we are in a situation where we've got a problem with plenty of modes, most of which have gone off. We've got plenty of modes, a set of light modes separated from most others by a big mass gap. Whenever that happens in physics, at least usually whenever that happens in physics, there is an interesting low energy effective theory of the light modes. And the point of this talk is to try to determine the effective low energy dynamics of these light quasi-nominal modes. Okay. Now, I haven't told you any details, but it turns out that the wave functions for these light modes completely localize within this small thickness region. The small thickness region I'll call the membrane region through this talk. Okay. For this reason, for various others, you might think that the effective theory of these light modes is effectively a theory of the membrane. Okay. The membrane is very close to the event horizon. We'll see this as we proceed. In this talk, I will try to show you how this works. We're going to use what you might think of as a collective coordinate method to try to understand the dynamics of membranes. What we do is reminiscent of the fluid gravity correspondence of the however, all our approximations for this talk will not be justified by long wavelengths, as was the case in fluid gravity, but by 1 over d. And so will apply to Schwarzschild black holes in flat space. Okay, so now let's start the technical analysis. We're going to find it useful to view the Schwarzschild black hole in so-called Kerr-Shield coordinates. Okay, Kerr-Shield coordinates, very nice set of coordinates for black holes. They have the nice feature that the metric of the black hole is written as a path that is just identifiably flat space plus something else. Okay, in particular for a Schwarzschild black hole, the Schwarzschild metric in Kerr-Shield coordinates is given by eta, which is flat space metric, plus n mu minus u mu, n minus u by rho to the power d minus 3, where rho is the function r naught by r, and u is the function for a Schwarzschild black hole in flat space, just the velocity field of the black hole, 1, 0, 0, 0, 0. 1 is in time. Okay, and r is the spatial radial coordinate. Now I've been a bit more fancy because I've written this in the written this Kerr-Shield metric not just for a Schwarzschild black hole at rest, but a Schwarzschild black hole at any relative motion, in which case u is just the velocity of that black hole, and r is appropriately defined. It's the distance perpendicular to u. Okay, great. This is just a rewriting of the Schwarzschild black hole. Fine. Now comes the important point. Now what we're going to do is to look at a metric that looks very similar if you just look at the symbols, but we're going to replace u, which was a constant one form field in flat space, we're going to replace u by an arbitrary one form field in flat space. Just anything that is varying, however we restrict to the fact that this u will vary on length scale 1. There's no d in the problem in u. Okay. Oh, I forgot to tell you what n was here. N was d rho, but normalized so that n had norm 1 in the flat space metric eta. Okay. So similarly here, we will allow this function rho, which in the case of the Schwarzschild black hole was r naught by r, is now allowed to be just anything, any slowly varying function. Okay. Yes. Why do I normalize it? I mean, I have to make a choice. Turns out to be convenient. We will see the difference between the flat space and yeah. Actually, one of the nice things about working with Kerr-Shield coordinates is this, that you can often regard the metric as entirely made up of quantities that naturally live in flat space. So you've got a one form field that naturally lives in flat space, a function that naturally lives in flat space, and then you deform the flat space metric by these flat space quantities. And this will be the point of view that we take, and it will be very useful. Okay, but we're coming to, this was your question. Okay, now this is just a metric, okay? It doesn't so far solve any equations, and you might ask why I'm writing it down. Well, I want to point out that this metric has two interesting properties. The first is the obvious one. This property is that if rho goes larger than 1 by any finite amount, then this metric reduces to flat space very fast. The same observation as what we had with the Schwarzschild black hole. How close does rho have to be to 1 before we start seeing that this is not flat space? Same as before. It has to be rho minus 1 has to be of order 1 by d. Okay? So outside a distance 1 by d away from rho equals 1, the surface rho equals 1 we'll call the membrane through this talk. So 1 by d away from the membrane, flat space, solves Einstein's equations. Great. Okay. The other property of this metric that's going to be crucial is the following. In response to Tom's question, let's compute the norm of the vector n, the vector that was chosen to be unit normalized in the flat space metric. Let's compute its norm in the actual metric. It's a 2-minute calculation to show that this is what you get. The important thing about this is that it vanishes at rho equals 1. Okay? Now n was proportional to d rho. So the fact that n's norm vanishes at rho equals 1 tells us that the surface rho equals 1 is a null manifold. Okay? It's a codimension 1 null manifold. Great. So we've seen two important things about this metric. Why are they important? First, let's look at the fact that this was null. Why was that important? See, let's look at the special case. We looked at general metrics of this form, but let's first re-specialize to the Schwarzschild metric. In this case, the surface rho equals 1 was, of course, a null manifold, but a very special null manifold. It was the event horizon of the Schwarzschild black hole. Okay, now, what we will see later on is that the equations that we get determining this dynamics will strongly suggest that in the future, all our solutions tend to either Schwarzschild black holes or Kerr type black holes, stationary black holes in the future. And this fact that rho equals 1 is the event horizon of these stationary black holes turns out to be true also for Kerr black holes, though I won't show it to you. Okay? So if we consider this metric subject to the condition that at very late times it settles down into some stationary black hole, then the manifold rho equals 1 is the null manifold which agrees with the event horizon at late times and therefore is the event horizon of our spacetime. Okay? So the manifold rho equals 1 is very special. Subject to this assumption about the future, it's the event horizon of our spacetime. Now there's a great thing about event horizons. Okay? Event horizons separate things inside from things outside in the sense that things inside the event horizon don't affect anything that happens outside. So if we want to solve Einstein's equations in order to give information to an observer observing LIGO type physics outside, we don't care what happens inside the event horizon. Okay, so we're not interested in solving Einstein's equations everywhere, we're only interested in solving Einstein's equations in the exterior of rho equals 1. But we've already seen that the equations are trivially satisfied for rho minus 1 much greater than 1 by d. So all that remains if we want to solve Einstein's equations is to look at these equations in a thin shell of thickness 1 by d around rho equals 1, the membrane region. Okay, so you already see that Einstein's equations are reducing in dimension. Okay, please.
You showed that the Einstein equation become trivial for a black hole.
Yes.
A Schwarzschild black hole.
Yes.
What about the waves that are rippling away?
Yes, we're considering particular solutions of what I'm going to try to do is to find a class of solutions of Einstein's equations. My class of solutions will be those that asymptote to things that are flat space for a long region, except for the radiation they cause. If you could postpone this question to the end, it will become clearer, I think. So please ask by the end.
Sarah was actually curious about what it was like in the interior, say, after the black holes collided or something. Are you saying you can't predict that?
I would say that my approximations would quickly break down, and then you would have to find, you're on your own. Good luck. Okay. Okay. Yeah. It's actually the same in the fluid gravity story. Yeah. If you look at, as you approach the singularity, depending on the length scale of variation, our solutions break down.
Well, I mean, as you approach the singularity, everything breaks
No, but it's worse than that. If you approach not within a Planck scale of the singularity, but with some classical distance of the singularity, depending on your wavelength of oscillations, the solutions break down. So that was a feature also of the fluid gravity map, because it doesn't affect the outside. Yeah. Yes. Okay. So now we've agreed we only have to look at this thin shell of this thin membrane region. Okay. And now I turn to a key point. The reason I've written my ansatz as I did after a lot of trial and error is the following. That if, I won't show you any details in this talk since I don't have the time, but if you write down Einstein's equations in this membrane region, and the way we actually do it is to zoom in on any point on the horizon, scale up all distances by d, and study the equations. There's an interesting large d scaling of the Einstein's equations. All this is great stuff, but I don't have the time to tell you about it. Okay, I'm just telling you the result, that if you look at Einstein's equations in the neighborhood, in this thin shell, this membrane region, you can show that our ansatz automatically solves the leading order Einstein equations in large D, provided these conditions are maintained. Provided the condition that the velocity field was not chosen complete, firstly, provided that this rho function was not chosen completely arbitrarily, but that it obeyed that 1 by rho to the power d minus 3 was a harmonic function on the surface rho equals 1. Okay. Moreover, that this velocity field here is normal to the normal. Okay, which means that it's a velocity field that lives on the membrane. Okay, and that the velocity field, regarded as a field that lives on the membrane, is divergence free. Provided these three conditions are satisfied, you can easily check that they are satisfied with the Schwarzschild black hole. Provided these three conditions are satisfied, this ansatz at leading order in large D satisfies Einstein's equations even in this little membrane region. Okay, and so we're going to impose these conditions in what follows. And then what we have is a good starting point for perturbation theory, because we've got a solution now, a configuration now, that solves Einstein's equations everywhere to the exterior of its event horizon, to leading order in large D. And therefore we can try to systematically correct this to find genuine solutions of Einstein's equations. Okay, now this is what I've said. If the ansatz solves the Einstein's equations at leading order in large D everywhere outside the event horizon, it can be used as a systematic starting point for perturbative construction of solutions of Einstein's equations order by order and 1 by D.
Are you saying the outgoing radiation is a 1 over D effect?
It's a 1 over D. It's a 1 over D to the power D effect. I'll tell you about it. It's very small at large D. I'll explain this. Okay. Okay. Now there's one technicality that's sort of irritating, but I have to tell you about, to be precise. Wow. Okay. Yeah, I need to hurry. And the technicality goes as follows. You see, I've got my spacetimes parametrized by, let's say, this function rho or this function u. These functions live in all of spacetime. But just because my ansatz metric here so quickly dies off as rho becomes large, what these functions are, the details of these functions at large rho, are essentially unimportant. Meaning two different metrics that have the same surface rho equals 1 and the same velocity field at rho equals 1 differ from each other only at subleading order in 1 over D, and therefore constitute equivalent starting points for perturbation theory in 1 over D. Okay, so our ansatz metrics can actually be labeled not by these functions but by surface data. And in order to make that precise, because to do calculations we actually need the functions, I impose an additional set of conditions, we call these subsidiary constraints, that completely determine these functions in terms of surface data. These are arbitrarily chosen, of course, after a lot of trying around to make the analysis simple. But you could have chosen anything. We choose these. Okay, we can now try to improve our ansatz configuration to ensure that it solves Einstein's equations to higher order in 1 by D. The basic strategy is perturbation theory. We add a correction to this metric suppressed by 1 over D and try to solve for it so that to ensure that Einstein's equations obey not to leading order but first subleading order as well.
Shiraz, are those conditions, is that some sort of gauge fixing?
It's fixing, no, it's not gauge fixing. It's fixing this subsidiary. You see, what we've got is we need a starting point for perturbation theory. Now, any two starting points that differ at 1 by D are equivalent starting points for perturbation theory, because perturbation theory will fix them up to the same thing.
So you're just pushing stuff around.
In that space, I'm making a choice. Okay, just that. Okay, fine. Now this whole process is only non-trivial in the membrane region, as we've discussed, and this is the bulk of our papers, but the procedure is complicated, but the results are easy to state. The perturbation theory in 1/d can be performed, but there is a constraint. It cannot be performed for arbitrary starting surfaces and arbitrary starting velocities. You can correct the ansatz to a genuine solution of Einstein's equations to next order in 1/d if and only if the surface and the velocity fields obey certain constraint equations. These constraint equations are written in terms of the extrinsic curvature of the surface, the velocity field, and the trace of the extrinsic curvature, and they're given by this, where this is a projector orthogonal to velocity. The really important thing about, I don't have the time to take you through the features of this formula, the really important thing about it is that if you go through the counting, you will find that there are as many equations as variables. Okay? So this turns Einstein's equations into a closed dynamical system for our membrane variables, namely the shape of the membrane and the velocity field. Okay? The integrability constraint for being able to perform the perturbation theory turns into a dynamical system. Okay, now we've iterated this thing to next order in 1/d. The result's more horrible. I just flash it here just to show you that I'm not bluffing you. Fine, and provided our integrability constraints are obeyed, we can also find the first order corrected metric. And it's a very complicated procedure, but in the end the result is extremely simple. To first order, this was the metric, this was the ansatz metric. To first order, we can only use one little correction, where that's given by this. So very simple metric, very simple equations of motion. Where is the d dependence? This kappa is of order d. The trace of the extrinsic, I would have to tell you a lot, but that's the d dependence. Okay, now everything I said can be generalized to the Einstein-Maxwell system. You start with not Schwarzschild black holes, but Schwarzschild. 10, great. You start with not Schwarzschild black holes, but Schwarzschild, Reisner-Nordst, whatever, the charged Schwarzschild black holes, and go through the same procedure. Now we've got one more variable, because in addition to the velocity and the shape, we've got the charge function in the membrane. So we should get one more equation. Firstly, the first equation gets modified with various factors of q, and then you get one more equation which governs the motion of the charge. Once again, we have as many equations as variables. By the way, this equation, if you looked at it, you would see that it's basically diffusion for the charge. Okay, so let us summarize what we've learned so far. We've established a one-to-one map between two dynamical systems. On one side of this map, we have black hole solutions to the Einstein or Einstein-Maxwell equations, whose event horizons do not crumple at length or time scales smaller than 1/d. Whose event horizon thickness is 1/d, but their variation is of order 1. On the other side, we have solutions of a non-gravitational problem. The non-gravitational problem describes a membrane moving in flat space. The degrees of freedom of that problem are the shape, a velocity field, and a charge density function on the membrane. Einstein's equations endow this auxiliary dynamical system with a clear set of equations of motion. Okay, you want to solve one problem, you can as well solve the other. As dynamical systems, they're completely equivalent. Okay. Yeah, in some sense, you can regard what we've done as a classical version of the ADS-CFT correspondence, justified in this for Schwarzschild black holes, justified in this case, unfortunately, by large d, rather than rather than long wavelengths, rather than low energies, and as we will see, radiation, basically the membrane modes decouple from the outside almost. Radiation reflects the breakdown of that decoupling, as we will see. Okay, now we've got these equations. Yes. What is special if d equals 3? Well, actually, if you see a number of our things, like we had 1 over, d equals 3 has no propagating gravitons. Something special should happen. You see it all over our formulas. Okay. Yeah. Fine. The membrane equations presented above are quite unfamiliar. For instance, there are no Schwarzschild black holes in d equals 3 in flat space. Okay. Yeah. The membrane equations above are quite unfamiliar, but in order to build intuition for them, it's good to look at special solutions. Let's first look at the simplest solution. Let's look at spherical membranes with spherically symmetric charge distribution and no velocity. Velocity is just, it's at rest. Because they solve the equations. They dual to the Schwarzschild or the Reisen-Nordstrom solutions that we started out with. Now we can do something a bit more interesting. Take the solution of the membrane equations, linearize the membrane equations around this configuration. You find a set of small fluctuations. These are the frequencies you find for these small fluctuations. Okay? The fluctuations with R represent, roughly speaking, of course they mix, but roughly speaking, shape fluctuations. The frequencies with Q represent charge distribution fluctuations, and the frequencies with V represent velocity fluctuations. Okay? When you look at these formulas, if you have the time to look at them in detail, you would see that each of them, except a very small number, have a imaginary part that corresponds to dissipation. Okay? The very small number that don't all have omega equals 0, and they're all zero modes. And the zero modes are exactly in correspondence with the known class of solutions. There's one corresponding to making the black hole bigger, there's one corresponding to changing its charge, there's one corresponding to translating the black hole, there's one corresponding to boosting the black hole, and most interestingly, as we will soon see, there's one corresponding to taking the black hole and starting to spin it up. So we have all the zero modes we expect, everything else is dissipative, everything else decays fast. Beautiful. Okay? So this shows you that this membrane system, these unfamiliar equations, at least linearized around these spherical bubbles, constitute a good, stable initial value problem. Okay. Now I've said all this. Okay. Now let's see if we can do better than linear analysis around some obvious solution. Let's see if we can find these rotating solutions that the linearized analysis suggested exist. It's very natural to try to, there's a very natural ansatz to try to find them. That is, choose the velocity to be that of rigid rotations. Constant angular velocity in orthogonal two planes. I've said that in formulas here. If you plug that into the equations, you find that all of these roughly D equations boil down to a single differential equation for a particular shape function. Okay, this is the differential equation for the shape function. I don't have the time to explain details. And that equation turns out to be easy to solve analytically in the case of uncharged black holes. We haven't been able to solve it analytically for the charge rotating black holes, which is a bit of a shame, but it's easy to solve either in perturbation theory or on the computer. Okay. Now, the duality we've just established could well have been called the membrane paradigm of black hole physics, except for the unfortunate fact that that name has been captured to describe what in my opinion is a less precise connection between black holes and membranes. Okay. Oh, this is great and I think very interesting. However, we've still not begun to address the question that we really wanted the answer to, namely, what will a LIGO experimentalist see if two black holes bang? Okay, a large D LIGO experimentalist, okay. 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 You might think that we're far from answering that question because, as you see, the metric and the gauge fields away from our event horizons decay very quickly. The LIGO experimentalist is far away. What does he see? Not much. Okay, so I want to understand precisely what he sees. In order to try to understand this, I need to take you through a 2-minute digression into the kinematics of Green's functions in a large number of dimensions. A number of you may know this well, but it was a surprise to me. So let's try to find the Green's function, the retarded Green's function of the operator del square in d dimensions. Turns out to be useful to work in position space and space, but Fourier space and time. Okay, for reasons, yeah, it turns out to be useful. If you do that, you take this Green's function at omega and make the rescaling with R that turns it into a Schrodinger problem. You find the following Schrodinger problem. Now, if you think about it, this Schrodinger problem is that of Schrodinger equation with a potential, and the potential is d squared by r squared, but it has energy omega. Now you've got this huge potential and energy omega. Radiation corresponds to tunneling through this potential. Okay, so this Green's function describes going through a huge potential, and then only what comes out eventually starts oscillating and radiating. Okay, you can say this in equations. You can say this in equations. That doesn't matter, I don't have the time for that. Okay, the key point is that there's this potential, you have to tunnel through a huge potential and then come out and radiate. And there are two important lessons from this. The first is that radiation, just for kinematical reasons in d equals infinity, is very small. You take sources of order 1 oscillate them about, they radiate very little. This tunneling in fact causes this radiation field, in fact the net radiation flux, okay, the net radiation flux to be of order 1 over d to the power d. Yes?
Clarify a little bit why it's frequencies of order 1 that's the relevant thing versus frequencies of order d?
Yeah, frequencies of order d, right, so very good point. Firstly, everything I say is correct for frequencies of order 1. Now that will be relevant to my question because all motions are on the time scales of order 1 for me. Okay? It would not be relevant to frequencies of order d, and that is of course due to the fact that Emperan ESTs, Emperan Suzuki Tanabe's fast modes are of frequencies of order d, and they blast through the membrane and radiate a lot.
But those might get excited if you collide two of these guys together.
Oh, they get excited, but you see these frequencies have an imaginary part which is also of order d. So they get excited and decay away very fast. Okay? So bang, a time of order 1 by d, you have nothing to say, and then our equations take over. Yes?
Order 1 and order d mean the order of the black hole size and the order of the near horizon. Right?
Correct.
Because otherwise you need the same.
Correct. Yes. Okay. Great. The other thing I wanted to say was that to excellent approximation, if your distance is order 1, this Green's function is just given by Coulomb-like falloff. Okay? It's just given by the decaying solution in this potential. There's a decaying and a growing part. The growing part is tiny. It's engineered so that once you reach here, it will have grown to be of the same magnitude of the decaying part. Then these two combine to give radiation. Okay? So at distance order 1, you've got basically the decaying part. But once you go out to distance order d, you start seeing the growing part and then you find radiation. Okay, so, oh my god, what's that? Okay, let's hope it works. Yeah. Okay, so we learned these qualitative lessons that I've told you about. Okay, great. Now, let's return to our membrane situation. In 2 minutes, okay. Let's return to the membrane situation. In the membrane situation, what we had was essentially the decaying part of the solution, the decaying part that's produced by these Green's functions. As you saw, all our solutions away from the membrane decayed away. As I've just told you, in order to find radiation, we need both the decaying and the growing part. One piece of information is not enough. It's a second order differential equation. Okay? So you might think that we cannot discover what the radiation will be unless we are much more accurate than we've been. But that's not true. Because you see, once you know the decaying part, there's another piece of information that will tell you what the growing part is. The information is that the solution has to be outgoing at infinity. Okay? So if you put that physical intuition back in the problem, there's enough information in our solutions to find the radiation at infinity. And in fact, when you go through it, it turns out to be, the best way to understand it turns out to be as follows. Radiation at infinity is given by convoluting a charge current with a retarded Green's function. The charge current is determined by the membrane paradigm, by our membrane equations to be this. And in fact, the second equation, the equation for charge distribution, turns out simply to be a restatement of the equation that this charge current is conserved. Okay? We haven't yet worked out the details for the stress tensor, but I believe it will be the same. There's a stress tensor on the membrane. The first equation is simply the conservation of the stress tensor, and that stress tensor is the source of radiation with a retarded Green's function. Okay, so now suppose I want to use this membrane paradigm to try to model black hole collisions in any dimension. What would I do? What I do is this: regard the my membrane paradigm as a black box that gives you expressions, constitutive relations for the membrane stress tensor. So forget about charge, there's no charge in LIGO, right? So the membrane stress tensor as a function of velocities and shapes to any order in 1 by d that you've gone. We've gone to second order in 1 by d. We've gone one higher order than I've shown you. Okay, then this stress tensor plays two roles. A, it's the equations of motion of covariant conservation, covariant conservation of the stress tensor determine the motion of the membrane. B, the stress tensor sources gravitational radiation. Suppose we've got two little bubbles coming together, each of them will be propagating in the field of the other guy. Okay? They'll come together, bang, bang, coalesce, except for the time of order 1 by d that Harlow was talking about, and then our membrane equations take over, this whole process emits its radiation. Hey, this is the way I would model black hole collisions using my membrane equations. Okay, so that's it. In this talk, we've established the classical version of an AD-SCFT type duality for Schwarzschild black holes. Unfortunately, this duality works only in the 1/d expansions, justified by large d, not by low energies. So it's not precise at any d, no matter how large. Okay. At large d, the classical gravitational dynamics of the black holes is dual to the non-gravitational dynamics of a membrane moving in flat space. The membrane is governed by a set of equations we've derived and are determined without any free parameters from Einstein's equations. Radiation reflects the failure of decoupling and occurs at order 1/d to the power d. The equations of motion are simply the conservation of the charge current and stress tensor on this brane. That's true for the charge current we know. That's true for the stress tensor as a guess, which we haven't yet worked out. These currents are also the effective sources for radiation. In our approximation, the radiation emitted in a complicated black hole process can simply be worked out by solving the corresponding gravitational membrane equations, non-gravitational membrane equations. This is a membrane paradigm, a sort of membrane paradigm for black hole physics. Thank you.
So questions? Okay.
I mean, I couldn't quite tell, so how hard are your equations to solve in the end? I mean,
Yeah, that we don't yet know. You know, all we've done is linearize them. Okay? So they're complicated nonlinear equations. However, let's note two things. There are two things among the many things that go into, you know, why are Einstein's equations with event horizon so hard to solve? For many reasons, but two reasons stand out. A, the Einstein constraints are difficult to maintain on a computer. Yeah. B, singularities that arise dynamically in coordinate systems are difficult to handle on a computer. Yeah. Okay? There may be many things. Note that both of these problems are not there in our system. We've dealt with all that stuff. Right? Okay? So, I think there is a chance.
Sorry, you've dealt with all that stuff in the case of one black hole.
But even with two, because our equation is completely local. So the topology of the event horizon doesn't matter.
But your coordinate rho equals 1, if there's two of them, will go over both.
Yeah, so there'll be a topology change, yes. Yeah. Exactly. So you have a function where rho is equal 1 here and here. Yeah. Okay, so we dealt with what two of the complications of solving Einstein's. Now, you see, I have absolutely no experience in solving equations numerically. The one time I tried, which was at Harvard, I estimated to my students we'd do it in a weekend. A month later, we still hadn't managed, then we got the experts to do it. You know, so you know, it's not something you do yourself. So
There's no problem when the rho equals one surface is coordinate.
no, there is a problem in the sense that the equations break down exactly at the point of coalescence. Yes. At that point, for a time of order 1/d, our equations are invalid.
How are you going to go through that?
I'm not totally sure, but what I was thinking was that we would just smooth out the solution there, but in some arbitrary way. You know, this is basically what would happen with soap bubbles. It's a question. Suppose you had soap bubbles that were breaking up, for instance, in a Rayleigh instability. At some point, the hydrodynamics equations don't fail. Atomic physics takes over. Very short time. Doesn't seem to matter for too much.
We know the probability is order 1.
What? Probability of what?
If the horizon touches it, the probability of order 1 is that it joins into a single.
Exactly.
It's exactly 1.
Yeah.
I think we have to stop. Okay. Yeah. No, we are running out of time, so let's move to the next second speaker. So let's first thank Shiraz.
Could I say one last thing? My last thing is to say happy birthday to David, and to just to say that my most vivid memories of David Gross was when he was in my thesis examination committee with the general exams in Princeton, when he was terrifying me by asking questions about tunneling through potential very much like this. For the problem of fusion, I think. Okay. Okay.